Okay, so let's implement the K-means algorithm from scratch. In the first, so today's implementation, we are going to implement this from perspective that is very straightforward, but it might not be efficient. That means we are going to using multiple for loops to calculate everything. But as we mentioned in the first week's lecture, if we use like too many for loops, this will significantly slow down our algorithms. So that means in the next lecture, as we're going to re-implement this K-means in the way that we are going to take advantage of vectorizations instead of using a bunch of for loops. But for now, let's just being very naive and implement everything from scratch with the for loops. First thing first, so this is the data that we're going to work with. We're going to work with this specific data. You can change this to 1, this is 0, so that means we are like muted for this like specific data. So you can see this is our and data. We have 1, 2, 3, 4, 5 different clusters. So this is quite difficult because for these 3 clusters, it's quite dense. So that means so the variances is small. And also for these 2 clusters, there will be sparse. So the variance will be high. It will be hard to capture all these 5 clusters. But let's see how does K-means work out. So so this is, we're going to work with the Euclidean distance, square of the Euclidean distance. This is just simply plot with the membership and also with the centroid as well. So this is my K-means function. So we have all these corresponding step 0, step 1, step 2, step 3 as well. So you can see what we do is we just randomly pick K different points as my initialization. So this is just will be my random and will be my initialization. Later on, we're going to optimize this part. So here, basically, what we do is we randomly sample this K points in my training data set. Then we are going to using this corresponding positions as my centroid. So for step 2, like 1, step 2, step 3, that will be in a gigantic loop. Here, I assume we have the maximum loop of 100. For now, I'm saying. So the step 1 is assign the samples to the closest centroid. That means we are actually creating the clusters. So the first thing then that we need to do is, the for loop work as we need to calculate the Euclidean distance between the samples and the point. So basically, we need to calculate the samples and the point 1 by 1. So this point is like, and those centroid, in the list of centroids. So basically, we need to calculate the sample point and all the centroids. So this will be your distance. So you choose the argument of the distance. That will be the corresponding cluster that, so this cluster should be assigned. So that means the cluster of the closest index, which is that corresponding cluster, I'm going to add this corresponding index. So this is very intuitive, just 1, 2, 3. This is just, and literally we turning the pseudocode into the actual Python code. Then also we need to calculate this distortion values. So this will be distortion values added with the minimum of the distance, which is corresponding to the distance of the point to this nearest or the closest cluster and the centroids. So this will be my and the distortion value. We add them up. So this will be my total distortions. If we want to plot, then we just plot it out. So this will be plot K-means. Step 2, we are going to calculate the new centroid from the cluster. Since we already update our centroids for all K different clusters with the different indexes that we created. So the first thing that we do is we're going to say my old centroid will be and save into, and we just copy the previous centroid into the centroid O. Then what we do is for each cluster, we are going to calculate mean of this points that belongs to that cluster. So this is the mean of X cluster. We take the average along the zero axis. So this will be giving me a row. And that will be my centroid with the corresponding and a cluster index. So this is nothing but just create and find the means for each cluster, which will be my new centroid. I'm going to append this like new centroid in the corresponding cluster index. The key here is for all the centroid that we have, and we have a centroid O that will be updated centroid. What we do is we are going to calculate the distance between old and new centroid for all k of that. If the distance is 0 for all the centroids, that means the centroid is like remain the same from the previous iterations. So that means it just remains the same. So that means my so my iteration has converged. It will just and then remain at this point. So I will stop. So that means that will be the stop. I will say the number of iterations is equal to k plus 1. Then I will break the whole iterations of this for loop. Okay, so like before that, we are going to also need to create the labels as well. So how we create the labels is we need to classify the examples as index of this cluster. So that means for all these points, and we need to create a dictionary. Here, our dictionary says, for each class, and we have all the index numbers. But here, and this is like inverse of the, and that will be the inverse of our dictionary. That means my label of that sample index in that cluster will be corresponding and a cluster index. So this is basically says we want to have a create and two lists. The first list is for each cluster, I want to know and what is the corresponding indexes. Right, so this is being given right here. On the other hand, for each like sample point, I want to know which cluster it belongs to. So this will be right here. To classify each samples as their index of the clusters. So that we have a two whole list, so we can use that based on our needs. At the end, we are going to output the label, cluster, centroids, and also this our distortion list. Here, I think I just run it once, right? So I mentioned before, you need to run this whole KMeans for 10 times with the random starts for 10 times and pick the distortion values is being the lowest out of this 10 and the 10 rounds. I didn't do that. In the next lecture, we're going to show how to do it. But in this lecture, we just want to demonstrate the main idea of the K-means and how to turn this like pseudocode into the real code. And we are not trying to optimize this whole thing at all, but just trying to and implement to see the performances. To see the results here. Okay, so if you do this for those data that we have, so this is basically how they work out and step by step. You can see this is my initial guess right here, right here, right here, right here, right here, which is not really bad, but you can see this is, we have a 2 and a 2 cluster here. And then let's see how it works. It start to move a little bit, right? It start to move a little bit. Gradually, it start to moving out of this region. Let's see how that goes. Okay, so at the end, it just almost remains the same right here. So we have a 2 and a 2 cluster right here and right here. Basically split this one cluster into 2. These is being the same, and I'm of 2 clusters. So this is not really a good example. So let me just rerun this a little bit. Okay, so this is six iterations. So like this turns out, and it did very good job with this good initialization. We have 1 initialization here, 2nd initialization here, 1, 2, 3. It turns out that we choose this initialization here, on the second iterations, it becomes like that because this becomes the purple cluster, this becomes the orange clusters. On the 3rd iterations, we find out this, and this is my orange cluster, this will be my purple clusters. And gradually they start to move out, and it becomes this big and cluster will be orange, this big cluster will be purple. At the end, it successfully identified this and 5 clusters perfectly. We have 1, 2, 3, 4, 5 with these 5 clusters after 6 iterations. So you can see from this performance, did a really good job. Right, and this is my centroid. This is my distortion values. So you can see my distortions values decreases and monotonically, except for the last one, but overall you can see it's and being very stable around this point. We can also plot this distortion values. You can see this actually decrease monotonically. At the end, we can plot the centroid. You can see this actually predict the centroid very well. It's exactly what we expected. And also we can doing some illustrations. And if we want to make predictions for new point, it will be assigned to the nearest centroid. So, and this is an Voronoi and Voronoi and a separation of the whole space by using the K-means. So basically, this is the plot with basically the decision boundaries of the K-means. So what does that mean is, if you have pick point right here, it will be classified into the members of the pink of this regions. Same here, if you in this regions will be classified as orange and so on. So this is basically Voronoi and the separations and Voronoi cells for these 2D planes. And this just give you how you make predictions and for each new point in the 2D planes. And of course, that's not really always the case. We can rerun this whole thing. And sometimes it will converge to what we want, but sometimes it will get stuck into other local minimum. And I want to remind you this distortion value. The final distortion value here is 493-ish. And let's see if this one values here. So after 17 iteration, it converges to this separation, which is not really ideal here. So it basically classified this 3 cluster into 1, one cluster here and the 3 clusters here, right? So this is not really ideal. But let's see this distortion value. I want to remind you, previous one is 493. But with this initial condition, this the last one get is 955. So you can see it's highly sensitive to this initial conditions. With this like specific initial conditions, my distortion value becomes 955, is significantly higher than the previous one. So we should not using this distortion value. As you can see from our and implementation, this is also really bad. And basically separate these and the one cluster into 3, but group 3 cluster into 1. So this is completely unnecessary. And we can plot this distortion list. It's still monotonically decreasing. By the end, this distortion value is significantly higher than 500. So we can still do this plot, but you can see this is not really ideal. We can also plot this and the Voronoi cell on this 2D plane by using this. But you can see this is the Voronoi cell with this specific and the local minimum of the K-means. And then this is my distortion values. So you can see this is significantly higher than the previous one. So that's why it is necessary. And I hope from these examples, I hope you can understand it is necessary that you need to rerun this 10 times to pick the one that with the lowest distortion values, because this whole thing is very sensitive to the initial conditions. If the initial condition is good, it will get really good result. If the initial condition is bad, you are getting something like this, which is not really good in terms of clusterings. Okay, so and we're going to talk about this a little bit more. There are 2 things that need to be discussed. The first thing, as I said, that initial condition is a big issue here. The second one is how to pick the K. Right here, I tell you we have 5 clusters, right? But if you are having the and a realistic data set, how do you know that you should pick K equal to 5, right? If you are given a data set, and how do I tell, or how do I test to find out the best case, just based on the data, right? So this is something that you need to consider in practice. All right, so this is the end of the first part, and on the next lecture we're going to talk about that for those 2 issues.